Here's a typical question I put on the Trig finals, and that's usually worth quite a bit of points. There are specific things I'm looking for, so let's solve this together, and next time you see this on the Trig final, you know what to do. There are two approaches to solve this one. Let's give you the fast one first. This one is what I call the flying method. Basically, the philosophy behind the flying method is to say, look, I have a sine curve. Sine curve needs really 5 points. Let's call them A, B, C, D, and E. And those 5 points happens when x is equal to, not x, let's call this angle inside equal to 0, 90, 180, 270, and 360 degrees. So what I can do is then think of this one as alpha. When alpha is equal to this, and those 5 angles, what I can do is to solve for where those x is going to be. I would have a new x1 that's corresponding to alpha xa, and then so on and so forth, all the way to xe. And then what I do is I will have a cardinal points graph. So there's x and here's y. Let's see, for example, for the first one is minus pi over 6. Okay. And when x equal to minus pi over 6, I plug it back in there, I'll have y is equal to 10. So all I need is point A, new point B, new point C, new point D, and new point E. I have 5 points. Then I can graph it. Now, this is called the flying method. Walking method, when I taught the class, is that I want to see the student be able to draw from the sine curve and using the different factors and location of those factors, either shift the curve left to right, up and down, squeeze the curve, and then shift magnitude-wise. Okay, so this is really walking or hiking method. It's really slow. However, just like hiking in life, it does give you a lot more details. Now, on the final exam, to make it painful for my student, I actually ask for both methods. Okay, so let's get to each one of them in more details. All right, let's get a clean space so we can start. Now, in the flying method, what's important is this philosophy of cardinal points. I know to draw any sine curve looks like this. I know I need to have 5 points. Okay, that's one period of this curve. What I need to know is where this new x and new y is. Okay, so each x1 pair becomes a point. So if I call this one alpha, when alpha equal to 0, alpha equal to pi over 2, and this is for alpha. Okay. Alpha equal to so on and so forth, so all corresponding to those 5 points, all the way to alpha equal to 2 pi, I can find what the corresponding x is. For alpha equal to 0, and this one is pretty easy to solve, it's minus pi over 6. And if I substitute back in there, I'll see y is equal to 10 plus 2 times sine of 0, which is 0. So my xy point, if I convert it into decimal, it's roughly minus 0.523, I believe, and 10. Okay, so in decimals. And I can do this for all the points, and once I have all the sets of 5 xy points, I can graph it. All right, so what I have over here is I solved a couple more points. And from the points, you can see I have this nice XY chart, X point and Y chart. And then I went to use the Wolfram Alpha, was it Mathematica, I believe. And here's the plot. So here's one point I showed on the graph, now corresponding to our chart. You can see we're going to get this sine curve. The sine curve was shifted upward. And that's because this factor of 10, and it was shifted to the left because this displacement. Let's get into this shift method and hiking method a little more detail next. Even though the hiking method is a little more involving and tedious, I really believe its value. The reason is that it shows more essence what the curve is really about. So let's investigate. Sine of twice alpha. This one just gets the curve up twice with the peak value of 2 and minus 2. So this one becomes 2. This old one is 1. That's all it does. Okay. Now what about 1 plus sine of alpha? The base curve does not change. The value, the entire curve moves up. Okay, this is as close as I can draw it. Touch down to 0 over here, and that's the 1 plus alpha over here. And then what about alpha sine of, say, alpha plus pi over 4? Well, that just shifts the curve, the green one, the yellow one, to the left. Let's see if I can duplicate it here. Okay, so basically, in this 3 class of curve, the base curve stays the same. Same shape. Okay, now let's take a look at what happens when the sine curve gets either squished, such as sine of 2 alpha, or sine of 2 and stretched. Okay, or alpha over 2 is what I meant to say. All right. So what happens when the factor is in front of alpha? This is a more interesting case. So you have sine of, say, let's say 2 alpha. Okay, because a sine curve finishes in 2 pi, and 2 alpha means alpha has to finish in pi. So here's the pi. Our curve has to finish within pi periodicity. So this result of this one is that sine of 2 alpha is a curve that got squished. Likewise, sine of alpha over 2 is going to be stretched. Let's see if I can plot it over there in color of white. Okay, so this is 2 pi. And then because alpha over 2 equal to 2 pi, alpha is going to finish in 4 pi. So this curve is going to be stretched out. All right, so here's the curve's shape does not stay the same anymore. All right, now let's combine those 2 pieces and take a look at our problem. So here's our problem. Now this one has got quite a bit of stuff going on. So let's take a peek at what we would have to do for this one. Now notice this factor over here, which signifies that 4 alpha basically it's squished. Okay, so we're going to do 4 alpha equal to 2 pi, which means the alpha has to be finished in pi over 2 pi over 4, which is pi over 2. So effectively over here on the green side, we have to finish this curve in 1/8 quarter of the space. So this curve is quite a bit squished. And then we have to move this curve to the left, pi over 6. Let's see if I can do that. Alright, so to signify this curve needs to move pi over 6 over. So let's see, it's going to be like this. And then magnified by 2 times. So let's get some height on this. And then the whole curve gets moved up 10. Oh, that's going to be a difficult one. Let's see. Let's say this is our 10 over here. The unit of 10. And then this whole curve is going to be sitting here on top of it. That looks like that. Okay, this is how we go. I apologize for this mess over here, but you get the drift of it. So you take a look at this 4 to squish it, and then you take a look at this to move, and then next to 2 is pretty easy. C's and D's are pretty easy. It's up and down and magnitude. All right, let's take a look at the computer-generated graph. All right, here's the computer-generated graph. As you can see, this curve is pretty squished. It's shifted over here a little bit, and let's see if I can magnify it a little bit for us to see. It's pretty squished because the factor of 4 in front of alpha, and it's shifted over by pi over 6, which is minus 0.523, I believe, and the whole curve is sitting on top of value 10. So here's the little shift here, and its overall shape is squished because the factor of 4 alpha. And here's the 10, and the magnitude is from 10 to 12, so this is the 2. Okay, so Correspondingly, this is the C. Let's see, this is the D going up and down. This is the factor of A, and here's that little shift is from the B. All right, this is pretty complicated, but I think it's well worth the time to investigate if it's the first time you sing it. Hi, this is Dr. Pan recording from Tucson, Arizona. Please comment or share this video. Together we can make math easy again. Have a confident day.